Hello, we are Team Radioactive. I'm Ankita.
I'm Alicia.
I'm Soham.
I'm Z.
And I'm Vishal.
We will be getting into our game's mechanics and features, as well as the interesting trends that we found after testing. Here's an introduction to our game. I'll first dive into a brief overview of our motivations for this project. In the context of games where players' actions have no real-life consequences, it's difficult to influence player behavior, especially in issues of morality. Our project focuses around priming, which is a concept in psychology describing how exposure to one stimulus may influence a response to subsequent stimulus without conscious guidance or intention. Priming's effects can vary in different scenarios, and in this project, we are aiming to investigate if priming, through a narrative provided prior to playing, can influence player behavior in relation to both morality and decision making.
So here are our two questions. The first one is, in the face of morally complicated and risky choices, what types of personalities will players' decision mirror after priming? And the second one is, can narrative priming impact player behavior in high impact and morally gray decision making, or will players default to their own sense of morality? So here is a brief introduction to our game mechanics. Our background story is you are a survivor in a zombie apocalypse. You live in a colony of survivors, and now you must take an ambulance outside and choose who to save. So here is our game interface. On the top, we have colony status, which we will introduce more in the following slides. On the left, we have brief description about each humanoid shown in the picture. It does not indicate whether the humanoid is a human or zombie. It only reflects the potential contribution you will make towards the colony. And also we have 4 actions. So skip, just basically abandon the humanoids. Squish, kill the humanoid. Save the humanoid to the ambulance. Scram empties the ambulance. And on the right, we have fuel value. So different actions cost different amount of fuel value. And if you run out of fuel or you don't have enough fuel to run another scram, then the game will automatically end. And also we have capacity, which indicates the limited capacity of the ambulance. So where each humanoid you save will take up 1 spot. And we also have 5 classes of humans. So first we have regular human. They basically can perform manual labor, but lack specialized skills. We have farmers. They specialize in agriculture, mainly for food supply. We have marksmen, specialized in weaponry, mainly for protection. We have doctors, specialized in medicine. They can treat wounded survivors. And lastly, we also have children. Currently, they will only drain colony resources without being able to contribute, but hopefully they will contribute a lot in the future.
So here's an overview of our narratives. We had 3 different modes with differing colony statuses, and the colony status reflects the current state of the colony. Rules and scoring across modes are constant. In mode 1, we explored negative priming, where we described the colony in an extremely dire state. The colonies were described with adults starving themselves to feed their children, little medical supplies, unable to save the injured to conserve resources, little to no security from zombie threats, and low morale and living on the brink of extinction. In mode 2, we explored neutral priming, which described the colony with a middling tone. The colony was described with enough food to survive day by day, hard but survivable lives, enough medical capability to heal moderate injuries, and enough healthy people to survive small zombie attacks, and unhappy but surviving people. In mode 3, we explored positive priming, which described the colony with an optimistic tone. The colony was described with a surplus of food for varied and healthy diets, low child mortality, strong medical capability, advanced weaponry to protect the colony, high morale and happiness, and long-term survivability. After data collection, we calculated 2 different scores, a utility value and an empathy value. The utility value calculated how much value you added to the community, and the empathy value calculated how much you're willing to protect the weak.
And now for our findings. So these were aggregated over 40 complete runs of the game, which included over 1,500 decisions being made. So first, this is a decision matrix showing what actions our players made depending on what human they saw. And this is specifically for negative priming. So some data points to point out are first, the extremely high save rates for both doctors and farmers, which seem to imply that because players are told that their colony is in such a bad state, they prioritize higher value professions. And something else to notice are the high skip and squish rates for children and regular people, showing that because these people can't provide that much value to their colony, they wouldn't be preferred in place of someone with a higher value. Now, for neutral priming, we observe some similar effects, but to a lesser degree. For example, the squish and skip rates for children and regular people both decrease, and there seems to be higher save rates for children and regular people, meaning that there's less of an influence on how much value they can contribute, and players seem to be more inviting towards all the different kinds of humans. And this effect is seen the most in positive priming, where professions seem to have no influence on how often different humanoids were saved, with both children and regular people having extremely high save rates, even beating the doctor. And in addition, the squish and skip rates for children and regular people drastically dropped. When players are told that their colony is in a thriving status, they don't tend to focus on how much utility people can bring to their colony, and instead they just save as many people as they can. And across these three different decision matrices, we had a p-value of 1.49 times 10 to the negative 8, showing significant differences.
So when we plotted utility score versus empathy score, remember these scores were not actually directly given to the players. We calculated them after data collection. We found some outliers, such as one in the bottom left, where a player tried to pick up as many zombies as possible in a run. But ignoring the outliers, it seemed there was a positive correlation between utility and empathy scores. Lower utility scores correlated to lower empathy scores and vice versa. Next slide. So when we calculated trend lines for the three priming modes, we found that there were different slopes for these trend lines, but we didn't have enough data to say they were statistically significantly different. So if we gathered more data, maybe there is a real difference between the strategies used in the different modes of priming. So here's a more detailed view on the utility and empathy scores for the three priming modes. We can see in mode 1, there tends to be much higher utility scores in green than the empathy scores in brown, as people are more utilitarian in the dire situation. In mode 2, the values are much closer, with utility in green and empathy in orange. And in the positive priming mode, it seems that the empathy score sometimes even beats the utility score towards the right side of the graph, with empathy in yellow and utility in light green. One other thing we noted was, on average, the mode 3 games of positive priming were much longer than the mode 1 and 2 games. A potential reason for this is people are more selective of who to save in the thriving scenario, as they have more resources to save the people who really need their help, rather than getting as many people with as much utility as possible back to the colony in mode 1 and 2.
Now let's get into some of the observations and conclusions we drew through the playtesting process. So on the left, we have some details about the conclusions from data analysis, while on the right, we have observations we had through playtesting. Many testers believed that the models of children did not elicit empathy because of the way they looked. But ironically, children tended to get saved more when the colony status was better and they were able to do so. People with better circumstances cared less about the actions they made, and as Vishal mentioned earlier, someone even experimented with picking up zombies. In addition, people who squished children, injured, and regulars regularly validated their actions verbally while doing so and seemed to enjoy the process. If we had time, here's a few things we would have explored. We would have made a few modifications, such as making it harder to identify humans, as that was not really a challenge for playtesters. We would also have less similarities between the skip and squish buttons. For future experimentation, we would like to explore more immersive or subtle priming effects, or also see the effect of changing class descriptions, as we noticed the harsh description for children especially affected how people viewed them. Here are our credits, and we like to give a special thanks to Jonathan, our TA, for all his help. Thank you for listening.
All right, so this is Team Husk's presentation over the zombie apocalypse game. It's by Harshal, Ethan, Charlotte, Moksh, and Shaurya. So just a quick overview of what we will be talking about. We're going to first dive into what we're researching or the question, then some new features we added to the base game, then some data we collected and the results, and finally some conclusions and insights. But let's talk about the base game and the research question first. So our research question was essentially based on the amount of information given, how do humans or AI models change their decision making in these ambiguous situations? So for some background, in the base game, you're in a zombie apocalypse and you're an ambulance driver with 10 spots available. Your goal is to save as many humans as possible. So as you can see, you'll either see a picture of a zombie or a human, and you choose to save it, squish or kill it, skip over it, or to scram and take everyone in your ambulance back home to safety. You have 12 hours to save as many humans as possible.
Okay, so now we're gonna go into some new features that we added to the base game that Moshe was talking about. So the first one is new utility classes. So we have separated, it's not just zombie and human anymore, but within that there's subclasses that have different aspects to each one. The first one is normal. It's just a normal human like Butters. What's up, Butters? The second one is doctor, and what they do is they carry a serum with them. So when you save them and you scram, you get a serum, and they're able to turn one zombie that you come across back into a human. So if you can save a zombie and turn it back into a human. The next one is thug, and what they're able to do is they're able to kill people in the van. So let's say you have 6 people in a van and you save a thug and scram. So the thug is gonna go through each of the other 6 people. It's gonna flip a coin. If it's heads, it'll kill them. If it's tails, it will not kill them. So it has a chance to kill everyone in your van or kill no one in the van if you're lucky. The next one is engineer, and they essentially just charge your time and upgrade your timer. So what they do is they add 120 minutes to your clock after you scram. So that way you get some time back from a run you had previously, and it allows you to keep going for longer. Now, imposter is the exact opposite. What they do is they take away time and sabotage your van so that you take away 150 minutes from the clock. The last and final one is pessimist, which is probably the most interesting one because what they're able to do is they're able to hamper other characters' special abilities. This adds another layer between the interaction and decision making in the game because not only will you have to think about the score when you come across this character, but you also have to think about how you would interact with other characters in the future based on what you decide to do with this character, whether it's saving or skipping it.
Okay, so apart from these utility classes, another major change that we added is making 2 distinct modes, easy mode and hard mode. So on screen right now, we have just a screenshot of our UI for easy mode. And the 2 main aspects that we circled here is that on the right side, we have this report which just displays the job class of the humanoid currently on screen. And we also have this button named reveal, which is currently disabled just because it's not used for this mode. But otherwise, the main difference is that you use these job classes to make a new decision, whether you want to skip, squish, save, or scram the humanoid on screen. And when we're talking about hard mode, the main difference is that we're now using probabilities instead of just direct classes. So now each human or zombie has a certain chance to be each role, and it's displayed by this distribution on the left side. So the chances are randomly generated for every single humanoid, and every single time it's just a different, again, probability of whether it'll be an engineer, a thug, imposter, or pessimist. And again, you have to use that information to make a decision each turn. And in order to combat this, in case you want to be more sure of your actions, we added the reveal functionality, which costs 30 minutes, but provides the actual job class of the human on screen. So if you want to be sure, and again, you don't want to use just the probabilities, you can use reveal for a little bit of a cost to have more, again, security. So combining all of this, we get hard mode, which now on the right side displays the probabilities instead of the direct job class and the reveal functionality for the action space. Now, discussing how we want to implement RL, we decided to use PPO or proximal policy optimization, which is just an architecture where we have 2 different networks, one which is the actor and one which is the critic, in which the actor decides what action to take at every single turn, and the critic decides how valuable these actions and states are. And over time, we hope to teach both of them to get smarter and to understand the environment better, and eventually want them to be able to, again, make the most optimal actions and understand the environment at the highest level. And overall, we had success with training it with over 500,000 time steps to get pretty good results.
Okay, so now here's the experiment we ran and some of the results we got. So for our experimental setup, we had several human playtesters play the game, And for each playtest, we randomly picked between easy mode and hard mode for the player to play first. The playtester played through the game, and we recorded each humanoid that they encountered and what action they took, and the score that they got at the end. And then we would repeat with the same playtester and the other game mode. And we also did something similar with our AI, except instead of just playing each mode once, the RL played each mode many, many times. So here are the score distributions for the human players and the RL model. So as you can see, for easy mode, both the humans and the RL had a pretty similar median score and pretty similar high scores as well. And for both, their average hard mode score was a little bit lower than the easy mode score. However, you may see that while the humans had a lot of scores in both modes that went far into the negatives, the AI basically had no negative scores at all. So the low scores of the humans were lower than the RLs. And also the RL had a couple very high scoring outlier runs on hard mode. And here's a breakdown of the distribution of actions that the humans in RL took in front of healthy humans. So the humans took a pretty obvious strategy to save all the normal humans, doctors, and engineers, and to just skip all the thugs, imposters, and pessimists. Because while those roles are negative, you also don't want to kill humans, as that will negatively impact your score. The RL took a pretty similar strategy, but instead of skipping pessimists, the RL actually saved most of the pessimists. And for a quick comparison of how they did in hard mode, for both the humans and the RL, their hard mode strategies remained mostly the same, except with a little more uncertainty. So all of the probabilities of the decisions are just a little less certain. And then now here's a comparison of the actions that the humans and RL took against zombies. So the humans, once again, had a pretty straightforward strategy of just squishing all the zombies, except the humans saved a few doctors and engineers. The RL, on the other hand, had a more complex strategy. So the RL squished some of the zombies, mostly thugs and imposters, but they also skipped some of all the zombies, and they scrammed in front of some of the zombies. And notably, the RL saved a lot of zombie engineers. And lastly, here's a quick comparison of how they did in hard mode. So the human actions against zombies in hard mode was actually mostly unchanged from in easy mode. They still just squish all the zombies at a pretty similar rate to easy mode. But in the RL's actions, you can see a little more of that uncertainty. No single specific action was chosen more than 40% of the time.
All right, so now we'll be going into the conclusions that we took away from this study. So in comparing the strategy between the RL and the human, we found that overall they had very comparable performance, but the RL and the human had very different strategies as well. For example, the RL was shown to scram a lot more often than the humans did, and the effect of that is they would get to apply the buffs more often, so that would signify that the RL prioritized the buff more than the humans possibly did. We also saw that the RL saved most of the humans, including the quote-unquote bad humans, so the pessimist, the imposter. So we found that perhaps maybe the RL would value the value of the human itself, which is 1 point, over its negative value in its utility. We also found that the RL valued the engineers a lot, to the point that it would even save zombie engineers, which might be one of the pitfalls that the RL fell into, because the engineer is a very powerful role, but it was not able to account for the fact that zombie engineers would not be as useful. And as for similarities, we found that both RL and human rarely used reveal. So this is definitely a signifying that that might be the best strategy given the game, to just not use reveal at all. As for future changes, we found that the reveal would cost too much. And when serving humans, as well as looking at our RL data, we found that most of them didn't want to use 30 minutes at all, since they found that it wasn't valuable enough for that amount of time. So we'd want to reduce it to maybe 15 minutes so that we can better look at the decision-making behind using that reveal function. We also found that the capacity might have been too large, so the humans would wait way too long before scramming, and a lot of the humans weren't able to apply their buffs until the very end. So we want to maybe reduce that to 6 so that we would force the humans to scram. And thanks for listening to our presentation.
Hello, we are Team Mer Zombie, and our final game aims to observe how the need to balance morale and survivability in a zombie apocalypse affects player and reinforcement learning decisions. My name is Jessica.
My name is Ryan.
My name is Anjali.
My name is SGAI.
This is a quick overview of what we will be covering today.
Before we go over the data that we've analyzed, we would like to go over the purpose and the mechanics of our game. As reinforcement learning becomes more mainstream in new technology like self-driving cars and robotics, it's been tasked with handling and maintaining multiple different factors and measures at the same time. In our game, we wanted to investigate the differences in humans versus AI in a zombie apocalypse environment, where they have to save as many people as they possibly can, while also maintaining ambulance survivability and morale. Some of the main questions that we hope to address with our game include how the RL model and the humans would balance multiple different factors, which end up affecting your end score, and how the human players handle the ethical implications of the situation.
To address these questions, we added special classes of humanoids as well as separate birds to balance. In a game, you're an ambulance driver trying to save people from a zombie apocalypse. While playing, you also have to ensure that the ambulance survivability and morale are high. If either of these two values drop to 30% or below, people in your ambulance suffer and die. During a search, you'll encounter a variety of scenarios. Sometimes it'll be more optimal to abandon somebody to keep the rest of the people in your ambulance well.
This is our game's user interface. On the left side of the screen, users can choose their action, which can be skipping, squishing, or saving the character. On the right side of the screen, you can see the remaining time left. You can also see the survivability and morale bars. And if any of these bars go below 30, people in your ambulance dying. If both of these bars have high values, however, saving a zombie will not result in the whole ambulance dying. On the bottom right, you can see the zombie spawn rate, which is the chance of a zombie spawning in your next turn. During playtesting, we also provided players with a chart so that they could see each action's effects. Some cases to note are that skipping a zombie will lead to a 10% increase in spawn rate, and the militants and celebrities affect both of the status bars.
Next, we'll be showing a quick game demo. As you can see from our demo, choosing to save a healthy person or injured person will increase your survivability and morale bars respectively, but saving a zombie corpse will decrease your morale. Our main models for celebrities are Spider-Man, Obama, and The Weeknd, and saving them will increase your morale while decreasing your survivability. Skipping them, however, will add 1 to your kill count, as they cannot sustain themselves in the city. Saving a militant, on the other hand, will increase your survivability while decreasing your morale. Players must then choose when to save or skip them based on the appropriate situation and strategy. If the sum of the survivability and morale bars are high enough, saving a live zombie will not kill everyone in your ambulance. However, skipping the zombies will increase the chances of the next character being a zombie as well. It is up to the players to balance survivability and morale while also keeping the final score as high as possible. In this demo, you will be able to see that the final score is 5.
Now we'll be talking about how we trained a reinforcement learning model. To measure the performance of reinforcement learning, we trained a PPO active critic model with 200,000 time steps over 120 epochs. As you can see on the graph, after training, the RL model on average saves 7 people. As opposed to the player, they get accurate information about what kind of humanoid they're currently facing and get immediate reward updates when they save zombies. The model has a relatively small observation space, allowing it to quickly train on our computers. In smaller tests, we've been able to achieve rewards of 5 to 6 with just 10 minutes of training. When training, the model can see the remaining time they have left, their current and previous reward, their morale and survivability bars, the actions they can take, and what type of humanoid they're currently facing.
Next, we'll be talking about our data analysis. We collected a total of 42 playthrough samples from human playtesters and 51 samples from our RL. The human distribution has an overall much higher standard deviation, as well as a much lower median and mean when compared to the RL. If you look at our summary statistics, you can see that the median for the humans is 1.5, whereas it is 8 for RL. When performing a two-sample t-test to see if there's a significant difference between the scores of the human playtesters and the RL, we received a p-value of 0.00031, which means that our results are indeed statistically significant, and we are able to reject our null hypothesis that there is no significant difference between the two scores. From each game round, we also compare the playtesters' final morale and survivability scores. Based on the following box plots, players' final morale score does indeed tend to be greater than their survivability score on average. Using another two-sample t-test comparing the distributions of each, we got a p-value of 0.014, which means that there is also a statistically significant difference between these two values. Similarly, we also compared the RL's final morale and survivability score. Based on these box plots, the RL's final morale score also tends to be greater than a survivability score on average, and with another two-sample t-test, we got a p-value of less than 0.0001, which means that there is an extremely statistically significant difference between these two values. Finally, we'll be talking about our conclusions and our future implementations. For prioritization, both humans and the RL model seem to prioritize morale more, and our t-test suggests that this is not just due to luck during their runs. There's an equal distribution of all characters spawning at the beginning, and interestingly enough, in our code, morale is more often negatively impacted. However, when we surveyed our playtesters after playing, more of them said that they would prioritize survivability in a real-life scenario. It's pretty interesting that the players weren't even aware of their bias towards morale, and this could be studied more in future implementations.
Other observations we noticed were the differences between the strategies of humans versus our reinforcement learning model. During playtesting, we observed that most players spent the first few games saving most non-zombies. However, they were able to quickly catch on to a strategy of only saving militants and celebrities when they had high enough percentages on their status bars. Around half of the players also tried to optimize the spawn rate by squishing zombies whenever possible. They also ended up always skipping zombie corpses. On the other hand, the reinforcement learning model saved and squished zombie corpses a lot during inference rounds, despite the impact on the score and their status bars. We think that this is probably because the punishment is too small to matter to the overall score.
So what might our conclusion suggest about the roles AI and humans can play in real life? It seems that while humans tend to perform worse in situations where multiple factors need to be balanced, reinforcement learning also isn't good at caring about emotions as long as the most amount of people are saved. Therefore, having solely humans or solely AI working on a multiple factor, high stakes situation may not be the best option. Though the RL is better at saving more people, it may not choose to make the most ethical decisions. So our game model suggests that rather than playing the main role, humans should instead aid the higher scoring RL model while checking its decisions for ethicality. In this way, the final score is going to be maximized while also maintaining ethical choices. Here are some things that we would like to work on for our game in the future. To begin with, we would like to make the RL model better and increase its best score by further training the model and fixing its hyperparameters. We would also like to explore how human ethics can impact their decision-making and how this knowledge is transferable into the real world. Experimenting on different methods of evaluating the reward can also prove to be extremely interesting. Currently, we only evaluate the reward by looking at simply how many people were saved or killed. We could further look into rewards regarding the time taken or the survivability and morale of the ambulance bars. Thank you so much for listening to our presentation. A big shout out to our TA Gabe, who was the best TA ever.
This is our Dead or Alive game by Team Hivemind, which is me, Vaishnav, Rosha, Chakri, and Anya.
So our motivation for our game was our curiosity about how humans' actions would differ from AI when placed in a high-intensity situation where lives are at stake. So our main research question was, how do machine learning models compare to human players in decision-making for maximizing colony value when given the options to skip, save, or squish zombies and humanoids? Our approach to address this question was using reinforcement learning to train a machine learning model, having both the human players and the model be constrained by limited ambulance capacity and actions that varied in time consumption, implementing a 5-second timer for each decision, and having players receive hints whenever a humanoid possessed a certain attribute.
For the UI, I added an instruction screen that appears when the player launches the game. The instructions include an overview of the game mechanics and the objectives for the players. And once the players have reviewed the instructions, they can press the play button when they're ready to start. The game interface now features a new health bar displayed on the UI, which shows the ambulance's health status. This health bar decreases by 10 every time the player squashes a humanoid, and the game will end once the health reaches 0. There's also a new clock added to the UI and a timer system. Players are given 5 seconds to make each decision. If they fail to decide within that time frame, the game will automatically force the player to scram, which shortens their turn. I also redesigned the buttons with a new display using Photoshop apps to make the game more visually appealing. Players will also receive hints when a new humanoid appears. These hints are derived from the metadata associated with each humanoid to help the players make a more informed decision and strategize their gameplay better. In terms of character models, I added new animations to the characters and hard-coded extra information, which is reflected in each humanoid's metadata. Each humanoid is organized into different categories, the most notable categories being zombies, children, and characters with occupations. Implementing the categories in each human's metadata basically allowed my teammate Vaishnav to assign scores and values to each one for our new scoring system.
So for the scoring system, we implemented a more strategy-based system than a moral-based system by creating a system based on long and short-term colony values. In this scoring system, humanoids would be assigned different long-term and short-term values depending on their attributes. So for example, a mechanic would have a higher short-term value as they'd be repairing the ambulance of the colony, while having a lower short-term value, whereas a child with potential to have a future occupation would have a higher long-term value, but shorter short-term value.
So we used RL to teach a model the most ideal decisions to make in our game situation. So the model basically had to choose to save, squish, or skip different humanoids. And the model received rewards or penalties based on its decisions. So if it saved a healthy human, which is a good action, such as a human with like an occupation, it received a reward. If it saved a zombie, which is a bad action, it received a punishment, which would basically tell the model not to do that action again. And over time, our model learned the actions that led to the best outcomes being the highest long-term and short-term scores, and it adjusted its behavior based on the feedback given to it through rewards and punishments. So this iterative learning process allowed the model to develop a strategy that maximized its scores in the game.
And these are our findings throughout 10 runs with the reinforcement learning model and 10 different human trials as well. So ultimately, the model averaged a final score of 377.5 total points, with an average of 165 short-term and 590 long-term, while the humans, as you can see in the graph, averaged a lower value of about 180-ish long and short-term. The model was also faster than a human player in making choices about the humanoids presented to it, as we saw from the timer data.
So we performed a significance test comparing the mean final reward of the reinforcement learning model and the mean final reward of the players. So our null hypothesis was that the mean final scores between them are equal, and our alternative hypothesis were that the means were not equal. We used the 2-sample t-test. Our test statistic was 2.828464. Our p-value was 0.011, which was below the significance threshold. So we do have statistically significant evidence that the means are not equal between the player and the reinforcement learning model.
So we found that the RL model seemingly performed better than humans according to the data collected. For example, the RL agent had scored 1,000 long-term value on its best run, while the highest long-term score for humans was 500. We also noticed that the RL model prioritized long-term score over short-term score, as can be observed from the RL's average scores. So from this data, we can conclude that it's possible that the model valued humanoids that gave long-term value much more over those with short-term value or no value at all. And humans, on the other hand, seem to prioritize both scores similarly or close to similarly. The RL agent was able to input actions significantly faster than the human playtesters when comparing decision times. So our 5-second decision timer didn't really seem to play a large factor in our RL's performance. But it's also important to note that this data may not be very statistically significant, since playtesters had someone from our group controlling the game for them. So their decision times may have been dependent on how fast the person actually controlling the game clicked the choice for them. In the future, to further this study, we could implement adaptive difficulty levels that adjust based on the model or human's performance. This approach would ensure that the model and human are consistently challenged, requiring them to learn and adapt to a wide range of scenarios. By having adaptive difficulty levels, we would be able to simulate the complexity of many real-world situations and collect even better data.
Hello, we are Team Regenerating from the Serious Games with AI course, and this is our project, Dead or Alive. My name is Daphne.
I'm Anvi.
I'm Aiden.
I'm Jessica.
And I'm Paul.
And our research question was, how do humans and reinforcement learning agents compare in playing a serious game with increasing levels of randomness? And we chose to study the difference between human and RL reactions to randomness because we were curious as to how RL will react to the unpredictability of reality, as they are usually trained in controlled environments. We were also partially inspired by how people interpret probability differently. For example, some people will always play it safe, while others like to take more risks. Next, we're going to explain our game. Its basic premise is that you are driving an ambulance during a zombie apocalypse, and your job is to save humans by bringing them back to a safe zone. And this is what our game looks like. We have action buttons, a humanoid, a clock that shows how much time is left, and a capacity meter that shows how many spaces are left in the ambulance. We used most of the base game functions, but one thing that we changed quite a bit was the visuals in Unity. We used Unity asset packs taken from the internet to improve the humanoid model and background. And because we changed the models, this is what our 4 classes of humanoids look like now. We have the healthy humanoid, the zombie, which looks like a human with green skin, injured, which is a human lying down, and corpse, which is a zombie lying down. And every time you encounter one of these humanoids, there are 4 actions that you can take: skip, squish, save, or scram. Skipping skips the humanoid on the screen, squish kills them, save adds them to the ambulance, and scram takes all the humanoids in the ambulance to a safe spot and clears a capacity. We also added a feature where if you saved a zombie, it would kill some humans in the ambulance as a penalty. Additionally, we also changed parts of the UI. To the base game, we added a menu screen and instructions and improved the original game's clock and capacity meter.
So in our game, each level introduces different elements of randomness. As you progress, the complexity and unpredictability increase with the addition of new mechanics. Level 1 is the foundation, where the main challenge is the varying timing of actions. These actions occur within specific time ranges, requiring the player to adjust and optimize the strategy accordingly. Level 2 adds a new layer of randomness, and we're in this stage, there's a 20% possibility that humans who are mildly infected during the apocalypse will fully transform into zombies. This increases the tension for players using the save button, as they now have to consider the risk of these potential transformations. Level 3 introduces another factor, a 50% possibility that the squish attempt might fail. And in this level, some zombies are too strong for the ambulance to squish successfully. So this encourages players to consider skipping zombies, which might save time compared to attempting multiple squishes that could end up being more time-consuming. Our scoring system is straightforward, with just 2 aspects, saved and killed. And you earn a point for every human you successfully save and scram, and the kill count increases for humans you squish or injured humans you skip. Now we will talk about the AI. Machine learning has 4 primary types. Supervised learning, where the model learns from labeled data to make predictions or classifications. unsupervised learning, where the model identifies patterns and relationships in unlabeled data, semi-supervised learning, which combines a small amount of labeled data with a large amount of unlabeled data to enhance learning accuracy, and reinforcement learning, where the model interacts with the environment, learning optimal strategies through rewards or penalties. For our game, RL is the best choice as it enables the model to adapt and optimize its actions in the dynamic and unpredictable game environment, which enhances performance through continuous trial and error.
So the environment is what our RL was interacting with. And our environment includes variables like capacity, time left, and the identity of the humanoid in front of us. The environment also includes an action space, which contains the action that the AI or the agent can take. And once the agent takes action, the environment will update and give the AI feedback, which it uses to learn. A Q table is a large multidimensional table where each element corresponds to a specific state. We can look up these states in the Q table to find out how valuable each action is and how much reward the agent can expect to get if it takes that action at each state. As the agent encounters new states and takes new actions, these estimates get updated until they are very close to the actual values. However, this requires it to see nearly every observation space to be effective and is thus too slow for us to train. So we can think of the Q table as a function where we input the state and get out the value of each action that can be taken in that state. And because it is a function, we can use a deep neural network to approximate it, which is what a deep Q network is. And our third type is the PPO, which stands for Proximal Policy Optimization. In it are two neural networks, an actor and a critic. The actor is the one that selects the action to be judged by the critic, which, like a deep Q network, computes the value of each state and gives feedback to the actor on whether or not it had chosen the optimal action. Because of this two-network system, PPOs are more stable and faster to train than Q networks.
So next we'll be going over our findings for both our human participants and the RL agents. So if you recall, at level 3, which maximizes randomness, squishing has a 50% failure rate, and we implemented this in order to give incentive to sometimes press skip or other actions instead of always squishing while faced with a zombie. And as you can see in the graph, the amount of skips on a zombie at level 3 was much higher than that of level 1 and 2, which shows how quickly participants were actually able to develop a new strategy when faced with this uncertainty. However, the expected value of time for the squish button was still lower than the skip button. We were able to calculate this using the equation shown on the slides. And it totaled to about 10 minutes for squishing, while skipping was still 15 minutes. So even though squishing was still more optimal than skipping, we believe that with more trials, our human participants would have also been able to figure that out and stuck with using squish instead of skipping. So continue with our human observations. The overall scores did not decrease as much as we expected with randomness. As you can see with the mean scores on the graph on the left, the line here is pretty stable and doesn't fluctuate very much between the levels. And we think this can be attributed to the ability of humans to adapt quickly to the randomness and change their strategy in order to face the new environment. Individual scores, however, as can be seen in the graph, vary significantly compared to the mean score, especially during the first few trials, which we think can be attributed to the player's exploratory phase, where they try new strategies and learn from them at the cost of a more consistent score. Although some of the scores for the humans were inconsistent, they were ultimately able to maintain a very high average score for all 3 levels, which shows just how well humans would successfully handle the randomness.
With those human observations in mind, let's start looking at some information about the reinforcement learning agent. So here we show 2 graphs for the PPO and the DQ learning, the DQN. So it shows the most popular or most chosen action in each level. So as you can see on the left, the PPO has a much more varied action usage than the DQN on the right, which is runs with one action the whole time. Now, this is quite interesting, especially for the PPO, because if you look at it again, there's an observation where we see that it actually squishes less on level 3 than it does on level 1 and 2. We hypothesize that the PPO learned similarly to some degree to what a human learned, that it's just not effective since you might have to squish multiple times, since there's a chance that it may no longer work. Now, with those actions in mind, let's look at the results from those actions. So here shows the graph similar to the one before, which Aiden showed. So we showed the average reward now with the PPO and the DQN. So as you can see, the DQN does really bad, and that's due to it just sticking with one action the whole time. However, the PPO actually did quite well, especially at level 1. We see that it does better than every human, basically. However, with increasing levels of luck in level 2 and 3, it starts to fall off and doesn't perform as well as humans, while the human is able to maintain and adapt to its environment. In conclusion, with this data, we see that at least our reinforcement learning agent performs worse than humans when there is an increasing level of luck. From that, we also had some other observations, our drawbacks. So first, our DQN. Our DQN had a really long training time, and that made us unable to train it to the degree that we wanted to. This may have been a cause to why I didn't really explore that much in its gameplay and couldn't adapt to its situations. So more training time could have made it done better. Also, our randomized time on the first level didn't impact human decisions, as humans often weren't minimizing or maximizing every action cost, and they just ended up not thinking about it very much. And level 2 did the same thing, where a human could turn into a zombie. However, this didn't present much of a luck-based dilemma, as when they did turn into a zombie, the human just acted in the way that they would act if it was a zombie. So in the future, we would like to add elements that also affected the human in terms of gameplay, as right now it might be slightly unfair to the human. And that's it for us. Thank you for listening.
This is Team Y's presentation, and we're going to start off with our problem and motivation. Our main research objective was that we wanted to specifically see how RL suggestions were able to influence players' decision-making processes when players were uncertain about their decision or were in a situation where they may have to make an ethical decision.
We were interested in our research objective due to the growing importance of human-machine teaming and interactions. Human-machine teaming is the collaboration and cooperation of humans and artificial intelligence systems to reach the optimal outcome for specific tasks or missions. For example, human-machine teaming is being used in high-pressure situations such as air traffic control, drone, military missions, and disaster rescue. In these missions, AI systems suggest actions to its human partner, which can take it based on data from previous missions. This allows human operators to expand their decision-making processes in critical situations. As human-machine teaming is being used more frequently in the military, it is important to ensure that humans and machines are compatible in high-stress, ethically ambiguous, and unclear scenarios in order to ensure the best solution not only for the defense industry, but the people it protects. This is why we were interested in researching human-machine teaming.
Now I'm going to talk about how our team approached the development of this game and how we designed the experiment. So in the original game, the player only had to keep track of time, but this version requires the player to keep track of both time and battery in order to save as many people as possible. So each action uses a specific amount of time and battery, and of course, running out of battery or time ends the game. So for the actions, the first one is skipping, which just skips the entity on the screen by driving around it, which takes more time than squishing because they're driven around rather than over. So we recommended to the play testers that this should be used when the user is unsure, but some players also decided to do what the RL said when they were unsure. Squishing, as I already explained before, crushes the entity on screen and takes less time than skipping. Saving places the entity in the back of the ambulance, and scramming transports every entity in the back of the ambulance to the hospital and saves the score, but it also takes the most time out of any action and restores your battery. We also gave the player 2 ambulance options at the start of the game to select from, which might affect their strategy when playing. So the first ambulance is quicker, except it has a 2 entity capacity and less battery life. And the second one is slower, but it has a 4 entity capacity and a higher battery life. And time and battery costs were given different multipliers depending on the ambulance chosen. And just to clarify, the speed of the ambulance impacts the time taken on each action.
Yeah, and overall, we have improved the UI to be more clear and usable, but some of the main additions include having the RL suggestion be given in a large speech bubble and having the corresponding button flash or blink to make sure the player understood the suggestion.
We also changed and add more human and zombie models in Unity, making some choices more ambiguous so the players could potentially rely more on the RL. Lastly, we displayed the age of the models on the left, prompting players to consider ethics when making a decision.
For our experiment, we decided to make the RL completely ignore the ages of the entities and ethical dilemmas. So in terms of playtesting, we split our playtesters into groups, either the control or the experimental group, in which the control group had no RL suggestions and the experimental group did. So we used this to see how often the player would listen to the RL versus making their own decision. But before the playtesters played, we brought their attention to a few things. So first we showed them the age indicator and told them they didn't have to save every human if they didn't want to. And we also informed them that the RL was just trying to assist. And if they were ever uncertain, they could skip. So we collected this data anonymously using generated codes and stored all the actions taken and other important game state data in the game logs.
So possible strategies that humans could have used were they could prioritize saving injured humans over healthy ones. They could prioritize saving children over adults, and they could also just follow every single RL suggestion.
Few other strategies we predicted were like players saving every human and squishing every zombie, or as I mentioned before, they could just follow the RL suggestion when they're unsure about the entity, or they could just completely ignore the RL.
Now we're going to talk about our results and observations. These bar graphs compare the likelihood of a player to choose the same action as the reinforced learning algorithm by action and group. Compared to the control group, the experimental group chose the same action as the RL more. This shows how the RL caused the players to change their instinctual actions to conform more to the RL suggested actions. The save and skip actions were especially affected by the suggestion. These are confusion matrices which compare the actions the players took, the actual action to the action the RL suggested, the predicted action. The highlighted diagonal line shows the times where the actual and predicted were the same. In the experimental data, we can see that the diagonal line showing the similarities is darker than in the control data in the highlighted upper left corner.
In order to find the extent to which players would follow the RL suggestions, we presented an ethical scenario within the game where certain humans were aged. With a space, time, and battery constraint, we wanted to see if ages of certain humanoids may influence player decisions. In the pre-survey, we asked if age should be considered in an emergency situation. Only about 14% of players said that it shouldn't. However, this statistic significantly changed in the post-surveys. While 40% of control players said that they considered age, 0% of experimental players said that they did. The experimental group had access to the RL suggestions, and the RL wasn't trained to consider age. This correlation between experimental players ignoring age and the RL not having access to age implies the experimental players got influenced by the RL's own ignorance to age, showing that in an ethically ambiguous situation, the age scenario in this case, players or human operators are likely to be influenced by the AI agent.
These survey results show that when players were put into confusing situations, such as not knowing whether the humanoid was a zombie or not, they would rely on the RL more than if they were very confident in their decision. This shows how the players used it when they were confused.
To expand on that point, this graph shows how people that were less confident in telling the difference between humans and zombies tended to have higher rates of having the same decision as the RL. This suggests that when they were uncertain about what to do, they relied on the RL suggestion more. Another research focus of our experiment was the human player's trust in the RL suggestion algorithm. As you can see in the upper right graph, people that were more trustful in the RL tended to have higher percentages of matching decisions with the RL, suggesting that they took the RL suggestions more often. This could also have two interpretations. Players who initially had the same decisions as the RL grew more trustful of the RL, which could create its own feedback loop, or people who trusted AI algorithms in general followed the RL suggestions more often. Interestingly, as you can see in the upper left graph, As players play more games, the percentage of matching decisions with the RL decreased slightly, suggesting that players became less dependent on the RL suggester as time went on. This goes against the modern trend of people becoming increasingly dependent on machine help and artificial intelligence. One theory behind this unusual pattern is that the RL assists players in the beginning when they are still learning, but as players get more skilled in their identification of entities or their strategy, they make more independent decisions. Another theory for this is that as time went on, players began to notice RL giving obviously wrong suggestions, and the players became less trustful of it. To determine which, if any, is correct, you would have to perform further experiments. Below are also some examples of what two playtesters thought of the RL.
So our final conclusion was that in ethically ambiguous situations and when confused with the encountered entity, players are more likely to take the RL's advice. The players then become less dependent of the RL as the game goes on, suggesting adaptation and learning.
There are many future applications of human-machine teaming, such as in the defense, aerospace, and medical field. For example, in the medical field, AI can help perform complex surgeries. This opens up opportunities for rising doctors to learn from their AI partners. This type of learning in human-machine teaming is likely to grow in many other industries in the future. However, the success of human-machine collaboration depends on how well we balance independent decision-making with fostering interdependent relationships. In our case, we observed that humans became less dependent on their machine partners as the task progressed. This may not be the case for every human-machine team. By creating environments where humans and machines learn from and support each other, we can enhance individuality and collaborative decision-making, ensuring the best possible outcome for human-machine teaming.
Thank you so much.